Welcome everyone, and thank you very much for your interest in my research. My name is Roberta Carluccio, and I'm a PhD student in computational geophysics. Today I'm going to provide you with an overview of the impact of an ultra-low velocity zone in the top asthenosphere on subduction dynamics. If at the end of this presentation you have any questions, please get in touch with me at this email address. So now let's go back to the nice science bits. We all know that the lithosphere and the asthenosphere have very distinguished mechanical properties. As such, the lithosphere implies a concept of strength and relative permanence, whereas the asthenosphere was originally defined as the weak layer of the upper mantle. What is new is that a range of more recent geophysical studies has suggested the presence of an ultra-low velocity zone in the top asthenosphere, which has been interpreted as a very low viscosity layer, possibly due to the presence of melt, hydrated, or volatile phases. An ultra-low velocity zone is predicted to lubricate the base of a plate and enforce the decoupling at the lithosphere-asthenosphere boundary, with important implication for our understanding of subduction geodynamics. Yet, little is known about the impact of an ultra-low velocity zone on subduction dynamics, and therefore we decided to simulate this impact using massive 3D numerical models of subduction. Little is also known about where these layers exist, and therefore we compile all observational ultra-low velocity zone for the very first time, and as we can see, this can be found in many subduction regions. Not only, but by compiling this information, we report a striking spatial relationship relating the presence of an oceanic plateau and an ultra-low velocity zone, which was also never reported before. When an oceanic plateau becomes ingested during subduction, this may result in complex geological and geophysical structures for which little holistic and predictive modeling exists. Therefore, we test the impact of an ultra-low velocity zone and an oceanic plateau in isolation and together on subduction dynamics, integrating our numerical results with geophysical observation. We find that surface motion, a range of slab and trench migration styles and pattern of seismic anisotropy can be obtained, including an ultra-low velocity zone, while an oceanic plateau can aid further complexity. By acting as a slippery base for the motion of that tectonic plate, an ultra-low velocity zone sharpens the decoupling between the lithosphere and the underlying weaker mantle. We can then reproduce quite well the dynamics of those natural subduction zones that fall into these regions, where plates move faster than their trenches retreat, for example in Mariana Izu Bonin, consistent with geophysical and geological observation of ultra-low velocity zones and oceanic plateaus. We hope these findings can provide a novel conceptual framework for the reinterpretation of the geological record of complex subduction margins. Thank you very much for your attention.